Planar networks and quantum immanents. And we're going to take Samuel out for dinner. It's 6:45 as usual place. Everybody's welcome, but you have to let me know right after the talk.
Thank you. So before I start talking about quantum immanents, I thought I would go over what classical immanents are. So we'll start by defining the symmetric group. So we can define the symmetric group as n to be the group generated by n-1 generators. With the relations, these generators commute if they're far enough apart. So I minus j is greater than 1. The generators si and sj commute with each other. Otherwise, if they're right next to each other, we have a grid relation. So I minus j equals 1. We have this relation here, si, sk, si, sk, and finally, all the generators are involutions. So si squared is always the n. And a class function or trace is just a function that satisfies functions with complex numbers from symmetric group that satisfies that f of wv is always equal to f of bw. That's the same thing as a class function, equivalent to just saying that it's constant conjugates of classes. All right, and so with that, I can define what an immanent actually is. This is not a super well-known definition. So an immanent, so like an F immanent, to the right, usually like this. It's a function from matrices to complex numbers, defined by we're going to take the sum over the symmetric group of f of the group element times the entry of the product of entries of the matrix given by this expression. So here A is an n by n complex matrix. And by W1 through Wn, I guess maybe I should say that with the presentation we were talking about this action of W as a permutation is just defined by like Si of x is equal to I if x is equal to I plus 1, I plus 1 if x is equal to I, and x otherwise. So those SIs are transpositions. So then F immanent is just, we take the sum over everything in the symmetric group, we apply F to the group element, and then we take the product of entries of the matrix, which we pick using that permutation. Add them all up. Okay. And why are people interested in these things? Well,
could you please lift the board? If
I can.
Yes.
Yep.
Oh, cool.
It's just.
Oh, much better. Thanks. So I guess maybe I should say the two most basic examples, or maybe motivating examples of an immanent are that the immanent of the constant function 1 is the determinant, and the immanent of the sine function, this is the permanent.
Yeah.
Thank you. And the immanent of the sine function is the determinant. Okay, so here the sine, this is just the constant function 1, and this is the sine of a permutation, so E of W is equal to the length of WL, where L is the length of shortest of a minimal or reduced expression. In these generators. So -1 to this is the sign. Okay. So these are a couple examples of immanents, and you can kind of think of immanents in general as like interpolating between these two extremes. And I guess I just wanted to give also a quick example of a classical combinatorial result about immanents, which is Lindström's lemma. So that's an evaluation of the determinant, which is an example of immanent. Let's erase this. So this is like the first combinatorial result related to immanents. And just stated, I need to talk about what a planar network is, a path matrix. So a planar network is just a graph, planar graph with two undistinguished vertices. I'm going to go through this really kind of quickly, but I'm going to be giving all these definitions again on the slide. So here we have an example of a planar network on 3 vertices, on 2n, so n is 3, and we've got 2n special vertices, which we label t1 through tn, and s1 through sn. And it's a directed graph. I'm thinking of it being directed left to right here. And the path matrix associated to A of f, associated to f, which we note A of f, it just records the number of paths connecting each source to the corresponding sink. So here in the 1, 1 entry will be the number of paths from source 1 to sink 1, which is compared to 1 path. There's also 1 path from source 1 to sink 2. Can't get from source 1 to sink 3 because it's directed edges. And there's exactly 1 path from every other source to every other sink. So, so I said you can record the number of paths, but in general, if you allow the paths to be weighted, and then these things record the total weight of all those paths in some sense, then this matrices that you get corresponding to all planar networks like that are totally non-negative matrices. And what Lindström's lemma says is for any matrix like that, we can evaluate the determinant of a matrix in a combinatorial way. Well, I guess for this sort of more simple case, Lindström's lemma would say that the determinant of this path matrix is the number of non-intersecting path families of type identity.
So that was later rediscovered by Gessler, do you know?
Yeah, so that's certainly the proof that I know of is Gessler-Vienna's proof. So I guess it's also sometimes called the Lindström-Gessel-Vienna lemma. So what do I mean by this? A non-intersecting path family of type identity is a way of choosing a path from each source to the corresponding sink. So S1 to T1, S2 to T2, S3 to T3, in such a way that none of those paths intersect each other. So you can see here in this example that there aren't any. Because if I have a path, there's only one path from S1 to T1, and only one path from S2 to T2, and those paths intersect each other. So you're not going to get a non-intersecting path family connecting all the sources of corresponding things. Okay, like I said, I'm going to give these definitions again, Q's on all of them. So this is the basic classical setup that we're trying to generalize. Okay. Questions about that? Okay, so the Hecke algebra. Hecke algebra has a very similar presentation to the symmetric group, well, the symmetric group algebra would be the group algebra of the symmetric group. So the Hecke algebra has a very similar presentation. It's generated over this ring of Laurent monomials in group Q, which we don't have to worry about that, it's just going to be Q's in this talk. And you've got n-1 generators again. Again, if two generators are far enough apart, they commute. So if I minus j is greater than 1, the corresponding generators commute. If I minus j equals 1, we get exactly the same braid relation. And here's where it's different. Instead of all the generators being involutions, we have this any generator squared is going to be equal to q plus q minus 1 times the generator you started with. So this is a q analog of the symmetric group in that if we plug in q equals 1, well, these two relations are exactly the same. And if we plug in q equals 1, this last relation will just become the same. Ti squared equals the identity. And so we recover the symmetric group algebra by finding q equals 1. And often people think of q as being like a root unity or anyway, this is just a parameter and stuff. So bit of useful notation, essential notation. Given a reduced word, so that's again a word of minimal length in the generates the symmetric group, we're going to define the corresponding element of the Hecke algebra to be just, so if we have this reduced word SI1 through SID, just take the word TI1 through TID, so just take the same product, sort of the corresponding product of Hecke algebra generators. It's not hard to see that this is actually well defined because of the fact that our relations are similar, and if it's a reduced word, we're never hitting that third relation that's different. And just also notation will say that TE is just the identity. So it turns out that this gives a basis for the Hecke algebra. So we have a basis for the Hecke algebra indexed by the elements of the symmetric group. Permutations. Okay, and again, we're going to make immanents using traces, which are defined in exactly the same way, except that now they're not class functions anymore, so we take this definition. Okay, so what is a matrix immanent? Well, quantum matrix immanent has to work. It's in a different algebra. So matrix immanent was a polynomial in the entries of a matrix. Quantum matrix immanent is going to be a polynomial in this quantum matrix by algebra, which is sort of like an algebra in entries of a quantum matrix, whatever that would mean. But in any case, we can just define it as an algebra generated over n squared generators, which we think of again as sort of being like the entries of a matrix. With these relations, the details of these relations aren't really important for the talk, but the key point about these relations is just that if you sort of look at what they're doing, they're allowing us to sort all the subscripts. So all of these relations, so this is like I is less than j and k is less than l. So in all of these relations on the left, we have something where some subscripts are out of order on the left, and we put them in order. Maybe we get some powers of q from that. Yeah?
Is it deliberate that the third and fourth rows have the same left-hand side?
No, that is a typo. Thank you. Yeah. Let's see. J, K, I, bolts. K.
So the only case
It's not actually K. They're going So the second subscript will be xjk. Is commutative? Commutative? xjk and xik.
Yeah.
Phenomenal.
So this is if these two guys are out of order. These two guys are out of order. This is the same. These are out of order. I think here is supposed to be the K's are here and the J and I are there. Thanks. In any case, but with those four relations written correctly, we can always sort any monomial in these guys into sort of a canonical order, possibly getting more monomials from this relation here and then powers of Q coming out. Right, so that's just what this says here. Call a monomial canonical if we've sorted all the subscripts into like lexicographic order. And because of the fact that those relations allow us to always do that to any arbitrary monomial, the set of canonical monomials gives a basis for the algebra. And now we want to talk about evaluating these polynomials on a matrix, which is a little more complicated than it was in the classical setting. So the way we're going to define evaluation is we're going to define this map. So this will be the notation that I use. So like sigma A, some polynomial here just means evaluating this polynomial on that matrix A. And the way I define it is I define it so evaluating a monomial, a canonical canonical order on a matrix, you just take the corresponding matrix entries. Just the corresponding product of matrix entries, and then you multiply by this factor, which is not really going to be all that important in the talk. And then you just extend that definition linearly to the rest of the quantum matrix algebra. So, in other words, if you want to take some arbitrary monomial and evaluate it on the matrix, first you've got to put it into canonical order, and then you just evaluate with these Q terms here. Okay, and that's all we need to define a quantum immanent. So, given a chain trace tau, we take the same almost definition. We just take the sum over everything in the symmetric group, apply our trace to the immanent, multiply by the corresponding product of matrix entry, or well, this is not the corresponding product of matrix entries here, it's the corresponding monomial. So x EW is defined just x1 W1, the product x1 W1 to xn W1. And then we have this factor Q here, which again I'm going to kind of sweep under the rug, but just for completeness sake, this is just Q to the length of W over 2. And so this is almost the same definition, except we're in this different algebra, and we have this factor of Q here. Okay, so that's a quantum matrix immanent. What kind of combinatorics can we do with these guys? Well, we're not going to be able to take any arbitrary immanent and evaluate it. So I'll focus on two families of immanents. So the space of Hn traces, it turns out, has a dimension equal to the number of partitions of n, or by a partition I just mean a weakly decreasing sequence of positive integers adding up to n. So we use this symbol or partition up. We'll say lambda, the partition is given by these numbers lambda 1 through n. And so the immanents that I will give formulas for are the ones corresponding to the induced trivial characters and induced sign characters of the Hecke algebra. I should say, when I keep saying the Hecke algebra, there's a lot of things that this is a very specific example of a Hecke algebra. That's the only one I'm using in the talk, so I'm just calling it the Hecke algebra. Okay. And I'm not going to define what these characters are, but I can tell you how to evaluate the immanents because it turns out that we have these nice expressions for them, which I'll show you now. Okay, so for a partition lambda, we'll let OSP be the set of ordered set partitions whose block sizes are given by lambda. And quantum permanent and quantum determinant are defined similarly to the regular permanent and regular determinant, except that we've got more factors of q. So here, right, so normally the determinant would just be -1 to this power times the corresponding matrix entries. And permanent would usually just be the sum of the matrix entries. So here we just added it, power of q to the -1/2 again, added power of q to the 1/2. And then with these definitions, I can say that the eta immanent, eta lambda immanent, is a sum over all the ordered set partitions of the product of these permanents of the submatrix of the algebra generators corresponding to the set partition. And the epsilon immanent, epsilon lambda immanent is the same thing but with determinants rather than permanents. So maybe I'll do an example of that. So let's say that lambda is partition of 3 given 2, 1.
And this identity is hard to prove, or the follow from definitions easily?
So that's a paper written by my advisor and a collaborator.
Oh, so it doesn't follow immediately from the
No, yeah, it's like 10 pages, I think.
It's a theorem.
Yeah, theorem. So these are not obvious identities. And I mean, I haven't even defined what those functions, eta and epsilon are, so I couldn't even begin to try to prove them here. But I can show you an example of how they work. So if lambda is equal to 2, 1, and n equals 3, the ordered set partitions corresponding to lambda would be, just we take the set partitions, order doesn't matter here because they have different sizes anyway, but we have like 1, 2, so I don't know, this notation is pretty non-standard, I guess, but here I just mean we have the set partitions where we divide it into the set 1, 2, and 3, or 1, 3, and 2, or 2, 3, and 2, 1, 1. And then, so for example, the eta immanent would be given by, well, we take a summand corresponding to this set partition. So then our first permanent would be the submatrix corresponding to 1 and 2. And then we multiply it by the permanent of the submatrix of generators corresponding just to 3. And then just write out the other two. And so, just to write that out completely explicitly, I guess, the permanent of this submatrix would be, well, x1, 1 times x2, 2, like it will ordinarily be plus, and this is where it's different. It's a quantum permanent, we get this factor here, so it would be like q to the 1/2 times x1, 2, x2, 1. And the permanent of a 1 entry submatrix is just that entry. And then, okay. Here, this permanent is just going to be x1, 1, x3, 3 plus q to the 1/2 x13, x31, and the last term will be x2, 2, x3, 3. And remember, this isn't like, it's non-commutative algebra, so it's important that these things be in the correct order. So then the eta immanent, we can immediately see, is given by the same exact expression, except instead of getting q to the 1/2, we're going to get negative q to the negative 1/2. And so on. Okay, so our goal then is to give a combinatorial formula for evaluating these things. And again, we're going to be talking about planar networks. We're not even talking about all planar networks. I'm going to talk about very certain types of planar networks, which end up being pretty useful. But so we're going to combinatorially define a family of matrices using planar networks. So a star will define Fij to be the directed planar graph with two undistinguished vertices, so it's a planar network, sources S1 through Sn and sinks T1 through Tn, where if it's the Ij star, we just connect all the sources I through j and all the sinks I through j with a star, and then connect all the other sources to their corresponding sinks just with an edge. So here's all of the stars for n equals 4. So this would be the star, the whole star 1 through 4. So we connect sinks 1 through 4 and sources 1 through 4 and sinks 1 through 4 with a big star. And that's it. Or the 1, 3 star, we connect sources 1 through 3 and sinks 1 through 3 with the star, and then all the other edges, or all the other sources and sinks, which is only one pair, we just connect to each other, and so on. So we got, I guess, F11, you could write, meaning source 1 through sink 1 is connected by a sort of trivial star, and then all the others are just connected by edges. So a couple things I want to point out. So I'm going to be dropping these vertex labels for the rest of the talk. So I wrote them here and then I stopped writing them, but you can always assume whenever you see any of these pictures that on the left we have vertices labeled S1 through Sn, and on the right we have vertices labeled T1 through Tn. And also, throughout the entire talk, all the graphs are directed from left to right. So when I say star, it's sort of the star with a choice of the direction on it. Okay, so there's 7 stars n equals 4. I guess F11, F22, F33, and F44 would all be the same thing. So that's a star. Oops. The descending star network is the type of planar network that we're going to be working with. And that's just given by a sequence of stars, arbitrary sequence, appearing in descending order. Concatenated with multiple paths collapsed. So for example, here we have a star, we have the star 3, 4, 2, 3, 1, 2. So those are descending order. Then we're going to concatenate them, and by concatenate I mean identify the sinks of each network with the sources of the next one. And then forget about those labels on the inside. So that what we end up with at the end is just a planar network here with 4 sources on the left and 4 sinks on the right. We're not really going to be worried about any of these. What may have previously been internal vertices. And then we do this one other move. So if we end up with multiple paths connecting a pair of vertices.
What does it mean descending order here? Descending with respect to what?
Just descending, so I guess it doesn't really matter how you do it. So so with respect to the lower index of the star, I guess you could say. So if it's Fi1, I2 here, or J1 here, and Fi2, J2 here, then I2 is less than I1. But it would work equally if you defined it with J being less. Um,